Hi everyone, this chapter is on light waves, so let's get started. These are the prereqs, and I have already covered them in my video Oscillations and Waves. Okay, because of the number of the topics, I'm splitting this video into two parts. So for this part, I will cover all the way from electromagnetic waves to curved mirror ray diagrams, and then for the second part, I will cover refraction through dispersion. Okay, so let's start with light. Light is an electromagnetic wave. We can also say it is an electromagnetic radiation. What are electromagnetic radiations? Well, they are composed of oscillating electric and oscillating magnetic field. I am not going to go into details. These waves carry energy with them, just like mechanical waves do, but there is a little bit of a difference between them. As we know, mechanical waves require a medium, but electromagnetic waves do not require any medium to transfer energy. This is why we can get electromagnetic radiations from this space, like we can get heat radiations, which we call infrared radiations from the sun, even though between sun and our Earth, most of it is just vacuum. Okay, let's talk about electromagnetic spectrum and trends. All electromagnetic radiations travel in waves, but different types have different wavelengths, frequencies, and energies. Visible light, which just means that light that we can see, is only a tiny part of this spectrum. So as we look at this image, we have radio, microwave, infrared, visible light, all the colors of the rainbow, ultraviolet, X-rays, and gamma rays on this spectrum. As we move from radio waves to gamma rays, the following trends are observed. I hope that this image helps you in noticing that trend. So wavelength, as we move from radio to gamma rays, wavelength shortens, frequency increases, energy increases, and speed stays the same. Okay, so let's quickly talk about it. From radio to gamma, wavelength shortens, as we can see that here. If wavelength shortens, frequency will increase. If frequency increases, energy is dependent on frequency, so energy will also increase. Speed has to stay constant because unless you change the medium, you are not going to be able to change the speed of electromagnetic waves or any waves. Okay, in terms of energy, how can you easily remember that energy increases? Well, remember that gamma rays, X-rays are dangerous radiations. When we are thinking about radio, microwaves, they are not dangerous, right? So hopefully that will help you remember that as you move from radio waves to gamma rays, energy increases. Okay, an interesting fact about electromagnetic radiations. Well, you have probably heard of the term radiation being used in a very negative way. Well, not negative, but we just think of radiations and we think of something dangerous, right? Now, not all electromagnetic radiations are dangerous. So let's talk about radio waves and microwaves. Radio waves carry signal for your television and cell phone and radios. Not dangerous, right? And when we think about microwaves, that is what you use in a microwave where you're cooking your food or heating up your food. The food is getting heated up by using the idea of resonance in water molecules. So the microwaves used inside a microwave box, those waves have the same frequency as the natural frequency of water molecules, and that is why water molecules will resonate it, which will increase the overall temperature of your food. Microwaves are also used to communicate. You can also take images of Earth by using microwaves. So there are lots and lots of applications of microwaves. Let's move on to infrared radiations. As you know, infrared radiations are heat radiations, but not all of them are heat radiations. Far infrared radiations are what we call thermal or heat radiations, and shorter or near infrared radiations are what we use in remote control. So when you are pushing the buttons on your TV remote control, they are just sending infrared radiations to the TV receiver, and that is how they communicate. So visible light waves are the only electromagnetic waves we can see. Remember, they are a very tiny part of the whole spectrum. We see these waves as colors of rainbow. Each color has different wavelength. Also, each color has different frequency and energy. Red has the longest wavelength, and violet has the shortest wavelength. In terms of energy, red has lower energy than violet. So if you compare a red flame to a violet or a blue flame, red flame is not going to be as hot as the other two. Okay, let's talk about ultraviolet radiations. You must have heard of these. You might have heard of UVA, UVB radiations. They're both ultraviolet radiations. And yes, they can cause skin cancer by mutating your skin cells. They cannot penetrate deeper than that, so that's why they can't harm any other body cells. When you're getting tanned, you're exposing yourself to UV radiations, and that is why your skin is getting tanned. But that also means that you are exposing yourself to those cancer-causing radiations. One cool thing about ultraviolet radiations is that we can use them to sterilize things because they kill microorganisms. Okay, let's move on to X-rays and gamma rays. You might have already heard of X-rays before, and it is possible that you got an X-ray done. They are used for medical imaging, but they can also cause cancer. And that is why the exposure to X-rays is very limited. It's also limited to the part that needs to be X-rayed. The rest of your body is usually protected by a shielding. The timing for which you are exposed to it is also very short. Now let's move on to gamma rays. You might have heard of gamma rays from Hulk. You're not going to become a Hulk if you're exposed to gamma rays. All right, gamma rays are very dangerous. They are more cancer-causing radiations because they can go through your entire body, so they can mutate all of your body cells. We also use them for radiotherapy. So yes, they cause cancer, but they're also used in curing cancer. The radiation therapy for cancer is what gamma rays are used for it. All right, this is the easiest one. Wave speed, we have already done it multiple times. We did it for oscillations and waves. We have also done it for sound waves. So wave speed given by V is equal to frequency times wavelength of the wave, right? All electromagnetic waves travel at the speed of 3 times 10 raised to power 8 meters per second in vacuum. Remember, that is the fastest speed. When these rays pass through some other media, their speed will change. All right, speed of light in air is very close to that of vacuum, so we can just approximate it to the same value. Speed of light only changes if the medium changes or the specific properties of the medium change. If the speed of an electromagnetic wave isn't given in a question, you can just assume that the question is talking about either air or vacuum, and you can just assume the constant value that we have and do your problem solving with it. All right, so here is a problem. The frequency of a gamma ray has been measured at around 3 times 10 raised to power 21 hertz in vacuum. What is the wavelength of this wave? So take a minute, write down your givens, and solve the problem. Okay, these should be your givens, and this should be your answer. Let's move on to light rays. So what are light rays, and why do we need them? Okay, light travels in all directions. In the given figure, only the two-dimensional representation is shown. You can compare it to if you were tapping on the surface of a body of water and you keep tapping at a constant frequency, you're going to start seeing the ripples. And if you took a picture of that, you will see something similar to what you see over here. Okay, so these ripples, we can call them wavefronts, and light rays are imaginary lines that are perpendicular to the light wavefronts. To keep the concept simple to understand, we usually draw light as rays instead of waves. The arrows on the ray indicate the direction of the light waves. Okay, the next topic we are going to talk about is reflection of light. Let's first talk about how are we able to see things. For us to see an object, the object should either emit its own light or reflect something else's light. For this class, we will only focus on the reflected light. The object also needs to be big enough to reflect light. For example, we cannot see air particles because they are too small to reflect light. In the same way, we can only see light if there is something to reflect it. To see a laser through air, you need to increase the particle size. In this case, we have used a fog machine to do so. So in this image, you can see that you can see the light rays. Actually, it is just a laser. So this is the laser incident on a mirror, and from the mirror, it reflects off. Okay, let's talk about mirror boundary and the normal. So when light traveling in one medium hits a reflective surface, that reflective surface could be a polished metal or a mirror. It reflects at the boundary. In other words, it bounces from the boundary. Same is true for curved mirrors, but because the surface isn't flat, it's hard to draw the rays correctly. The normal line helps minimize this error. Since normal is an imaginary line, we draw it as a dotted or dashed line. Okay, so and normal is a line perpendicular to the plane at a point on the plane. You might have heard of this in your math classes, but you might not have. Okay, so if you look at a flat surface, the dotted line is the normal at a point, and that line makes a 90-degree angle to the surface. But when we do that for a curved surface, you can see there is a difference in the surface, but the normal line can still be drawn. If we can visualize each small section of the surface as a flat plane, our surface normal will be a straight line exactly 90 degrees to the center of that plane. Okay, these are images of flat mirrors reflecting light. Okay, let's talk about drawing a ray hitting a flat mirror. We can visualize how light interacts with surfaces through a ray model of light, which states that light will travel in a straight line forever until it is obstructed by matter. When a light ray, which we call incident ray, reaches a mirror boundary, it will be reflected, and we call that ray a reflected ray, and it will begin to travel away from the surface at the exact same angle. The illustration gives us context as to how light will behave when interacting with a flat, smooth, and highly reflective surface, such as a raw, polished metal or a mirror surface. You can see incident ray came in, hit the mirror, and it gets reflected by the mirror. The angle that the incident ray makes with the normal is called angle of incidence, and the angle reflected ray makes with the normal is called angle of reflection. Okay, so this is what that diagram looks like. We got our incident ray, we got our reflected ray, we got our angle of incidence and angle of reflection. Please note down these terms because they will be used regularly in ray diagrams and you need to be familiar with them. All right, let's move on to law of reflection. It is very simple. It is just like common sense. If you throw a tennis ball at the floor at some angle, it is going to bounce off in the other direction, but at the same angle. The same way, when light hits a surface, a reflective surface, the angle of incidence is going to be the same as angle of reflection. Okay, let's move on to flat mirror ray diagrams. The purpose of these diagrams is to predict with accuracy where an image will form and what it will look like. Images are always formed where reflected rays intersect. So this is what a point object's ray diagram will look like. You just have to follow these steps, and if you don't have a point object, then you just pick another point and repeat all of these steps for it. So for just a point object, you will end up with 2 incident rays, 2 reflected rays, 2 normal rays, 2 virtual rays, and then you will find your image. The reason we draw the virtual rays is if reflected rays don't intersect on this actual side of the mirror, then you have to extend them back, and we call them virtual rays. Just to keep things simple, we only talk about spherical mirrors. Types of mirror that we will work with are concave mirrors and convex mirrors. So if you're standing on this side of the mirror and the mirror is curving away from you, we call it a concave mirror. But if the mirror is curving towards you, we call it a convex mirror. Okay, so these are the three images of a flat mirror, convex mirror, and concave mirror. You can see that a flat mirror doesn't really diverge or converge the reflected rays. A convex mirror will diverge the reflected rays, and a concave mirror will converge the reflected rays. And that is why sometimes convex mirrors are called diverging mirrors and concave mirrors are called converging mirrors. These are a few terms related to spherical mirrors. So center of curvature is the center of the sphere from which the mirror is cut. Focal point is the midway point between the mirror and the center of curvature. The principal axis is just a straight line that connects all of them. Okay, let's look at the rules for drawing curved mirror ray diagrams. When drawing curved mirror ray diagrams, the law of reflection still holds true, but we can't really use it directly because it becomes almost impossible to not make errors. So what we have done, we combine the law of reflection with some geometrical rules, and then we come up with these three sets of rules. Okay, now if you follow a textbook, another website, another teacher, you might end up with completely different sets of rules. They're also going to be true, but these are the three that I find the easiest. Okay, so you will draw three incident rays. The first one is going to be parallel to the principal axis. Then you're going to draw the incident ray that passes through the focal point. The third one is the one that passes through the center of curvature. For these three incident rays, the reflected rays, for the first one will be the one that passes through the focal point, the second one will be parallel to the principal axis, and the third one will be just the one passing through center of curvature. Okay, and wherever these three reflected rays meet, that's where the image will form. Okay, when you're doing curved mirror ray diagrams, so if you are given a question, the question has to give you the principal axis, mirror, focal point, and center of curvature. These need to be already drawn for you, and then the object will be placed somewhere on your principal axis. The reason this needs to be already given, because you actually have to draw them correct geometrically. Okay, so just follow the steps that I have given earlier, those rules, and you should be able to draw this diagram. So we start with our first incident ray that is parallel to the principal axis. It reflects through the focal point. The second incident ray goes through the focal point and then reflects parallel to the principal axis. And the third one goes through the center of curvature and it reflects back through the center of curvature. So it's just a line that is just on top of the other line. Where those reflected rays meet, that is where the image of the top of the arrow will be formed. If you need more instructions on other type of diagrams where the object is placed between center of curvature and focal point, or between the focal point and mirror, please follow the link that will take you to the other video of curved mirror ray diagrams. Okay, so this is what your image should look like. Then we talk about the properties of the image. So your image can be inverted or erect. It can be magnified. It could be diminished. It could be real or virtual. It will be inverted or erect. Well, those are simple words, right? Inverted means it is upside down. Erect is the right side up. Diminished means smaller. Magnified means bigger. Real means that the image is formed by real reflected rays. Virtual means that the image is formed by virtual reflected rays. So in our case, our image will be inverted, diminished, and real. Okay everyone, we have reached the end of part 1 of light waves. I hope you enjoyed the video and you learned a lot of physics about light waves. Thank you so much for watching. I will see you for part 2.